I won't do that. When we start fall semester, you all are jumping right into clinic. So there are some fundamentals that I want you to have a basic understanding of relative to image quality and looking at some of these factors. We will spend next semester going into detail with these factors, but for right now, you do need an overview so that you have an idea as to what the technologists are talking about when you start out here. Oh gosh, just a couple weeks away, about 3 weeks away. So that's what we're going to do with this particular PowerPoint. It's just kind of get your feet wet with some of these terms and being able to understand what's going on here. So we've mentioned this before, right? Haven't we mentioned this? Right. Our imaging goal is to have optimal diagnostic information, but we need to keep patient exposure to a minimum. So we want a very good diagnostic image, but we need to be mindful of how much exposure that patient is receiving. So that's our goal. And we have to achieve a balance. We need that quality image, and we have to reduce radiation exposure. And it is a balance. It's a balancing act. Okay? It's a balancing act. If your exposure factors are too high, it can be detrimental to the image. And of course, that's increased exposure to the patient. If our exposure is too low, well, yeah, that you may think that's great for the patient, but then our image isn't going to look right. So then in actuality, you end up increasing patient exposure because you have to end up repeating that image. So it is a balancing act. You do need to know the factors that come into play for achieving a good image and protecting the patient. So we've got these factors, MA, exposure time, KVP, SID, OID, collimation, grid, part thickness, and collimation. These are exposure factors, right? These are things that we can control, we can manipulate. Okay? In terms of patient factors, we really can't manipulate these. Now, we can a little bit in terms of part composition. We can add contrast media to a body part, but that has to be protocol for a particular exam. You just don't decide to add contrast media to the patient. And then, we've looked at the prime factors. We looked at MA, exposure time, KVP, and SID. These are considered to be the prime factors for radiation exposure. All right, so let's kind of review the prime factors, just a quick overview of them. MA, remember, that's the current or electrons in motion, and there you've got what it's equal to. And again, on a test, I won't ask you this, but it's just to show you the impact and how many electrons are moving per second. And there are various MA stations. Again, our equipment, it does have MA stations, but it's behind the scenes. We're not actually setting them, but the X-ray unit is setting them. These are just some examples. 50 MA, 75, 100, 150 MA, 200, 300, 400 MA, 500 MA, 600 MA. And then the exposure time, that's in seconds or milliseconds, and that's the length of time the electrons will flow across the tube. So the MA and the time gives us the X-ray quantity. In fact, when you multiply MA and time, so and assuming that time is given in seconds, if it's in milliseconds, you have to convert to seconds first, because MA and time will yield mass. This is our milliamperage seconds. And that is the total number of electrons that are flowing across that X-ray tube. Okay, so that's our tube current. That's our mass determines that tube current. And that ultimately determines the number of X-rays that will come out of that tube, what gets produced. Okay. And so the relationship with that quantity, remember, it's direct and linear. So if I double the mass, I double the number of electrons, so I double the number of X-rays that are produced. So it's a direct and linear relationship, and that's why we look at mass for controlling receptor exposure. And just a reminder, if you have X-ray equipment where you can set the MA and time, the general rule of thumb is highest MA, shortest exposure time. Do you remember why? What's the significance of that?
To decrease
So who remembers
patient
that?
exposure.
Pardon?
To decrease patient exposure, or no, I'm sorry, to decrease the time the patient has to sit still for.
Right. You want to decrease the chances of patient motion. Right, exactly. Of course, with our equipment, since it's most of these nowadays are falling load generators, the unit is deciding the MA and time behind the scenes. But the unit typically, it will start at the highest MA so that the shortest time can be used. So we had looked at mass. We looked at KVP, that's that force that drives those electrons across the tube, and it's also referred to as potential difference, tube bias, electromotive force. We mentioned that term. So those are just other names that are synonymous with KVP. KVP is the primary controlling factor for quality or energy. So here you see, a difference in the energy of the X-rays. Higher energy X-rays, lower energy X-rays. So this means this was a higher KVP, this was a lower KVP. So primary controlling factor for energy. The KVP, though, also has an impact on quantity. Okay? It also impacts the number of electrons that are produced. It's very important that you remember as the KVP goes up, the electrons have an increase in energy. They have a higher KeV. So remember, the electrons here that boil off the filament at a higher KVP, the electrons have a higher kinetic energy. So why do we end up with more X-rays being produced? What is the significance of the electrons having a higher KeV? What's that significance? If they have more energy, more interactions. And you all had this question on the test. At a higher KVP, the electrons can undergo more interactions at the anode because they have more energy to give up. So they can undergo more X-ray production interactions. So that's how it impacts the quantity. Why is it not the controlling factor? For quantity.
Because mass controls the quantity of what comes out of the tube.
Okay, it's true, mass does control quantity, but why? I mean, KVP impacts quantity, but why don't we use this as our controlling factor? We did the experiment in lab. We did that tube output experiment where you measured.
You're talking about doubling exponential instead of linear?
Right, it's more exponential, so it's harder to predict. Yeah, we know if we increase KVP that the quantity goes up, but it's hard to predict, exactly and by how much. Okay? So we don't want to use that to control it. And also, too, since KVP controls the quality, we have to make sure that we are using the proper KVP for the body part that we're imaging. Okay? In terms of exposure factors, this is another prime factor. These are our typical source to image distances. And remember, though, that SID has no impact on X-ray production. SID has no impact on the number of X-rays that gets produced, but it does impact receptor exposure. Why does it impact receptor exposure? What is that law that has the math formula with it?
Inverse square.
inverse square law. Inverse square law. Because remember, as distance increases, you still have the same number of photons. It's just that they're spread out over a larger area. So you have fewer photons per unit area. So SID, it only impacts receptor exposure, does not impact what comes out of the tube. Right? So those factors were a review for you. Now we've got some other factors that we need to take a look at. We have something that's called OID, and OID is object to image receptor distance. So it's object to image distance. So, from the patient's body to the image receptor, that is the OID. The rule of thumb is in medical imaging, we always want to have the shortest OID possible. We always want the image receptor to be as close to the body part as we can possibly get it. Okay? So OID needs to be as close as possible. And we'll be taking a look at this. Collimation, this is another factor that we can control. Collimation reduces the X-ray beam to the part of interest. Here we've got a wider primary beam than what we do here. We've collimated. Why is it important to collimate when possible?
Reduces scatter and exposure that's unnecessary.
Mm-hmm. It will reduce the amount of scatter that gets produced. We'll be looking at that. Yeah, absolutely. And it reduces exposure to the patient. Okay. Grids is another factor you'll be dealing with. Grids, they're composed of lead strips. They will absorb scatter radiation, but you have to follow protocol for using a grid. And these are just some examples of different sizes and shapes of grids. But the grid is located under the tabletop. Or if you're talking about the upright unit, like we have in our lab, the upright units against the wall, there's a grid in there too. We can also use grids when we do mobile imaging. So we have portable grids as well. And so we'll be talking about grids, but that's something else that you'll use according to protocol. Okay. So those are all the factors that have an impact on receptor exposure, and we refer to those as our exposure factors. Now here we've got patient factors that come into play. Part thickness, we've talked about. Part thickness will play a role in the exposure factors that we set because different part thicknesses have an impact on the receptor exposure. Part composition. Now, this is supposed to be a lung field, and this is, an abdomen here. But the part composition, what that part's made of, is it primarily bone, or is there a lot of soft tissue? Is there air in there? That plays a role in the exposure factors that we set and how much exposure gets to the image receptor. So you don't use the same set of technical factors on an abdomen that you use on the lungs because we know that there are differences in attenuation here. So that's kind of an overview of some of these factors. We'll look at some of these, a little more detail. And like I said, next semester in particular, we will. All right. But why don't we go ahead and let's just take a 10-minute break. Let's see, what is it? 10:56. I tell you what. Go ahead and make it easy. Come back at 10 after, and we'll roll through some of these, and then depending on how you all do, maybe we'll end around 11:30. So when you come back, maybe we'll do about 20 more minutes. Okay, would that be all right with you all? Okay.